In this example, the people are on a space station. So it's a rotating space station shaped like a bicycle wheel. And forgive my poor drawing here, but you can kind of imagine this is looks like a bicycle wheel. The actual space station is this little space here. So the people would be kind of here and here and here. And their feet are kind of like on this outside wall, okay? So there's their head and then their feet are down this way. There's their arms. So this person would say up is this way. This person over here would say up is going this way. So kind of towards the center of the circle for everybody. For this person, towards the center of the circle is up. Everybody would point towards the center of the circle and say up. So the ship is rotating that way. It's going around, or the opposite way. It doesn't matter, but it's going around in circles. And kind of like if you can imagine a little bit of water in a bucket and you're swinging this bucket around, when the bucket goes to the highest point, the bucket is upside down, but the water doesn't fall out because of this spinning, because you're spinning. And if you didn't already watch the video in the lesson, it says something like 2001 A Space Odyssey or something like that. There's a ship in an old movie. Anyways, it has a rotating part like this, and you can kind of see the person is like running around the outside. So it will kind of show it well, I think, what's going on here. Okay, so in this case, the interior radius of the space station, so like this radius here, this radius is 2 kilometers, 2,000 meters. It's going to rotate so they have an apparent weight of 1/2 of their weight on Earth. Okay, so what that means is apparent weight is normal force. If a question tells you something about you feel like you're half your normal weight, or your apparent weight is, I don't know, half your normal weight or something like that, what they're saying is normal force, which is typically equal to Fg, is now equal to half of Fg. Okay, so your apparent weight, your Fn, is equal to half of your weight on Earth. Your weight on Earth is Fg, there's half Fg. As long as that part's okay, then this question isn't too hard. So just like we're doing with all these questions, Fc is equal to mv squared over r. We know in this case, so let's say like there's a person here, let's use this person right here, or maybe let's like a dot here. There's a person here, there's a normal force going in this way towards the center of the circle. We saw this on a couple of the other questions that we've done. There's a normal force kind of going in towards the center of the circle as they go around. The floor is keeping them in, preventing them from flying away. There is no other force. There's no force of gravity here because we're out in space. Okay, so this is a space station. There's no Fg, no force of gravity. What that means is the only force acting to make this centripetal force, the only force acting is Fn. So Fn equals mv squared over r. What we've said right here though is Fn is equal to half of Fg. Okay, so 1/2 Fg equals mv squared over r. Fg, typically on Earth, Fg would equal half times 9.8. Okay, so we're not on Earth, we're out in space. But remember, this is I equal half of my Earth weight. Okay, so the magnitude of my Earth weight is my mass times 9.8. Just keep in mind, this here is also my mass. What we're talking about is the person, or whoever this astronaut is. So let's say if it's me, then it's my mass that is whirling around. So the mass that goes here in the center, or here in this circular motion thing, that is the mass of the astronaut, or whoever we're talking about that's going around in circle. Oh boy, how do you spell astronaut? No GHT? Just a T, right? So this mass and this mass are actually the same mass. Okay, so mass of astronaut, they can cancel out. We could then bring r over here, so 1/2 times g times r equals v squared. What we're looking for is speed, that's what we're looking for. If I turn this around, v is equal to 1/2 times 9.8 times the radius of this ship. Remember, 2 kilometers is 2,000 meters. Don't forget, don't forget this thing is squared. Well, let's put the squared here. We'll say square root on both sides. In which case, v is, what is that? It's about 99 meters per second. With two sig digs, I guess. So the trick, I guess, in here is just knowing this. Apparent weight is your feeling of weight, your feeling of weight comes from the normal force. That's why if you're on a, let's say like in an elevator, and the elevator starts to go down, if the floor of the elevator drops out from beneath your feet, you feel a little bit less heavy than you normally do because your normal force changes. It's not your FG that changes, it's your FN that changes. For part B, we're looking for the period of rotation of the spaceship. So there's a couple ways we could do this, but one way is we know that speed is distance over time. If you can imagine, if I start here and I go all the way around once, the distance that I cover is actually the circumference. Okay, so I'll just write circumference. If I go exactly once around, one circumference, then the time that that takes me is called the period. Okay, so this isn't always true, but if I'm going in circular motion, if I go once around, then the distance that I cover is the circumference, the time it takes me is my period. Circumference of a circle is 2 pi r. Period is just capital T, that's period. What we're looking for is period. Okay, so that thing right there. So if I rearrange then, 2 pi r over v, 2 pi, radius was 2 kilometers, so 2,000 meters again. V is going to be this 99 meters per second that we had from over there. In that case, period, it's approximately 127 seconds, and we could do something for sig digs there, 1.3, if we wanted 2 sig digs, 1.3 times 10 to the 2 seconds. But about 127 seconds.